So for example, let's take a disk. So if we have a disk, we're going to rotate the disk. Actually, let's take more like a hollow cylinder. So like a ring, if we rotate the ring, right? So even if the ring's not physically moving, like linearly speaking, it's not rolling, okay? The ring itself, we would say, has energy because it's moving. What kind of energy does it have if it's moving? Kinetic energy, right? It has some kinetic energy. So what if we were to look, say, at just a single point right here, a single mass, single like point mass on the ring, and I asked you, well, what's the kinetic energy of that little mass? How would you find it? Ke equals 1/2 mv squared, right? Because this has a velocity, a linear velocity as well at that point. We could just say, well, Ke is equal to 1/2 mv squared. Okay? So notice also that the mass is moving rotationally. So it also has an omega here. Well, what's the relationship between the v at this point and the omega? V is equal to r omega. Right? V is equal to r omega. So let's go ahead and make that substitution here. We'll substitute in for the v. So we'll have 1/2 m r squared omega squared. Okay? Well, this is moving, this little point's moving in the circle, so we also say it has a rotational inertia. Anyone remember what the rotational inertia is for a point like a point mass? Okay, I is equal to mr squared. Well, take a look at our equation here. We have mr squared. So we could write this as 1/2 I omega squared. So this is our equation for kinetic energy rotational. And again, if I asked you ahead of time to guess what the equation was, you probably would have come up with this, right? Because we have I, remember m and I, these are kind of the equivalents. And v and omega, these are the equivalents as well. So this would be the kinetic energy. So if something's moving like this, spinning around, it has a kinetic energy that's equal to its inertia, proportional to inertia, and the square of its angular velocity. All right? So let's do a problem here.